आज के इस विश्लेषण में we are tackling a classic engineering mystery. Welcome to the explainer. So, picture this. You're sitting in a really high-stakes electrical engineering interview, right? And the interviewer throws a scenario at you. On the surface, it seems, well, incredibly simple, but it's actually designed to completely test your foundational conceptual clarity. It's literally the kind of question that separates the total novices from the true experts, and we're going to unpack exactly how the whole shebang works.
So here's the exact scenario they hit you with. What happens if a three-phase induction motor gets a one-phase supply? I mean, really think about it for a second. Will it still run, maybe just kind of slower? Will it instantly overheat and burn out? Or will it just sit there humming at you? This is absolutely the ultimate conceptual test for any electrical engineering interview. We're going to break down exactly what goes on inside that motor, why the physics play out the way they do, and exactly how you should answer this if you're ever put on the spot.
Well, here's the blunt truth. Right off the bat, it won't start. No way. If you hook up a single-phase supply to a three-phase motor, it simply will not go into rotation. Technically speaking, absolutely zero starting torque is produced. The motor will completely fail to turn. But, to truly understand why this heavy, expensive piece of machinery essentially turns into a giant metal paperweight, we have to first look at how it's actually supposed to operate under perfect conditions.
Okay, let's dive into this. Section 1, the power of three-phase and the ideal state. Walk through this logical sequence with me. Step 1, the three-phase supply is applied to the motor. Step 2, and guys, this is the absolute magic of three-phase power. It effortlessly creates a rotating magnetic field, or RMF for short. Imagine this perfectly smooth, invisible magnetic wave constantly sweeping in a continuous circle right around the inside of the motor. Step 3, as this rotating magnetic field cuts across the motor's rotor, Faraday's law of electromagnetic induction kicks in, inducing an electromotive force, or EMF. Finally, step 4, this induced EMF produces torque, which confidently and smoothly spins that rotor. The entire system operates beautifully, just like clockwork, but it depends entirely on that sweeping, rotating magnetic field.
Now, what's really interesting about this next part is how we meet the core villain of our story. Section 2, the single-phase dilemma. Let's directly compare these invisible forces. Over on the left, our three-phase supply is giving us that perfectly smooth, sweeping circle of a rotating magnetic field. It's directional, right? It has this momentum that just pulls the rotor along. But take a look at the right side with the one-phase supply. A single-phase system fundamentally cannot create a rotating field. It just can't. Instead, it creates what's called a pulsating magnetic field. So it's not sweeping in a nice circle, it's more like a frustrating back-and-forth judder, just expanding and collapsing in a straight line.
And because we're dealing with a pulsating magnetic field, we get a phenomenon known as pulsating torque. Basically, this is a force that alternates rapidly back and forth without actually creating any net rotational movement. Essentially, your motor is completely confused. It's being told to go clockwise and counterclockwise at the exact same time with equal force. So what does it do? It just intensely vibrates and hums super loudly, completely paralyzed because it literally cannot pick a direction to actually spin.
So the crucial point is, if we trace this invisible chain reaction, the domino effect of a one-phase supply is pretty catastrophic for rotation. The first domino falls. There's zero rotating magnetic field. That knocks over the second domino. A pulsating magnetic field is created instead. The third domino goes down. That pulsating field generates pulsating torque. And bam, the final domino, the rotor simply locks in place. The energy is absolutely in there, inside the motor, but without that rotating field to guide it, it's entirely incapable of causing any actual rotation.
But we all know actual single-phase motors exist everywhere in the real world, so there has to be a fix, right? That brings us to Section 3, the capacitor solution.
And this brilliantly illustrates our way out of the problem. If single-phase power only creates this paralyzed pulsating torque, engineers figured out they could, quote, artificially create a second phase. It's an absolutely brilliant mechanical hack. By wiring a little capacitor into the circuit, they manipulate the electrical current, effectively shifting it to trick the motor into thinking it's actually receiving a second distinct phase of power.
Visually, we can see exactly why that artificial phase is the missing key. On the left, one phase alone leaves us stuck with that locked rotor and pulsating torque we just talked about. But look at the right side. When we combine the original single phase with the artificial second phase created by our handy capacitor, those two overlapping forces interact. They generate what engineers call a resultant torque. And this resultant torque, Let's move to and see how this builds into Section 4, cracking the interview.
We've built all the conceptual clarity now, so it's time to bring it back to that high-stakes scenario we started with. Here is your exact summary script, so you can confidently deliver it to an interviewer. First, you state that a three-phase supply creates a rotating magnetic field, which is totally essential for smooth rotation. Second, a one-phase supply fundamentally cannot do this. It only creates a pulsating magnetic field, which results in zero net torque, meaning the motor won't turn. Finally, to bypass this limit, a capacitor is required to artificially create a second phase, generating a resultant torque to initiate rotation. Delivering this crisp summary shows you don't just memorize basic facts, you truly understand the core physics at play.
It really is amazing how a simple, inexpensive little component like a capacitor can literally trick physics into getting a heavy motor spinning. And this brings us to a really fascinating question to leave you with. If a capacitor can so elegantly create an artificial phase out of thin air to get things moving, what other inherent limits of single-phase power can clever engineering bypass? Think about that as you reflect on the concepts we've covered today. Thank you so much for joining me for this explainer. Keep asking those deep questions, and I'll see you next time.